This video describes the derivation of the most famous equation in science. In 1905, Albert Einstein published 4 significant technical papers, one on Brownian motion, one on the photoelectric effect, one that became known as his theory of special relativity, and one on the equivalence of mass and energy. Special relativity superseded Newtonian mechanics by explaining how the speed of light with respect to any inertial reference frame, any reference frame that is not accelerating, is constant and is independent of any motion of the observer or the light source. Einstein's 4th paper can be summarized by E equals mc squared, where E stands for energy, m stands for mass, and c is the velocity of light. C has a value of 299,792,458 meters per second. This is a large number, and when you square it, you obtain an enormously large number. Even a small amount of mass represents an enormous amount of energy. The equation is famous because it led us to understand the source of the energy that causes stars to shine and how they could shine for billions of years. It also suggested a source of power for use on Earth, and then in turn the development of the most powerful of weapons. But this was not obvious in 1905. The structure of atoms was not yet understood. This was more than 20 years before the discovery of the neutron. I was majoring in physics in college. Like many, I was intrigued by this equation. Yet in all the courses I took, I never encountered a complete mathematical explanation of where E equals mc squared comes from. These explanations, of course, do exist in many different places, but most often the explanations start with the formula for the relativistic mass increase with velocity. I'll not assume that here. This video starts from scratch and derives E equals mc squared. The viewer is presumed to be comfortable with algebra, geometry, trigonometry, and simple calculus of a single variable. It is also assumed that the viewer has taken an introductory course in physics. The derivation makes use of many of the concepts in mechanics: vectors, velocity, relative velocity, momentum, acceleration, energy, the law of conservation of momentum, and the law of conservation of energy. This video is accompanied by the PowerPoint presentation from which it was recorded, and by copies of some of the more detailed mathematics. None of the work here is original. The references I used are listed at the end of the presentation. If you follow the sequence of discussions in this video, you will understand how and why we know E equals mc squared. Our agenda then is as follows. We start with electromagnetic waves and why their mathematical representation requires C to be a constant. We then discuss the Michelson-Morley Experiment, which is the most famous of many experiments to provide data that shows C is a constant. We follow with an interpretation of the Lorentz transformations for position and for time. We calculate velocities using these transformations and discuss why we mean that time is relative. Next, we derive the equation for relativistic mass with velocity. This is done by making only the assumptions that momentum is a vector in the same direction as the velocity and that momentum is conserved during an elastic collision. We finish by deriving the equation E equals mc squared using calculus. If you are familiar with differentials, taking the derivative of a product of two functions and the chain rule, then the derivation is straightforward. This video is long. I did not learn all this material in one sitting. I did not make this presentation in one sitting. I do not expect that anyone encountering this material for the first time will watch this video all in one sitting either. But if you think physics is exciting like I do, then this video will provide a great example of how the mathematics that is used in physics is beautiful and I will bet then that you will enjoy the video. This slide shows a representation of a light wave of a single frequency traveling through space. The wave consists of electric and magnetic fields that are sine waves of the same frequency. The sine waves are perpendicular to each other and to the direction in which the light wave is traveling. In 1865, James Clerk Maxwell was the first to propose that light is an electromagnetic wave that travels at a constant speed c in a vacuum. The speed of light c is related to two fundamental physical constants in nature shown here at the top right: the permittivity of free space, an electrical parameter, and the permeability of free space, a magnetic parameter. The electromagnetic field waves obey the four relationships shown at the top left. These relationships are called Maxwell's equations. The symbols in the equations refer to vector operations called divergence and curl. These operations involve vector calculus and are used to express the first-order partial differential equation shown here. For the purpose of this video, it is only necessary to know that these equations were known to exist in the late 1800s and that they were gaining acceptance in the scientific community as a complete description of all electric and magnetic phenomena. This slide shows two more partial differential equations, one each for the electric field E and for the magnetic field B. They follow logically from Maxwell's equations. These are called second-order partial differential equations because they involve taking the derivative of a derivative. These equations for E and B have the exact same form as the equation at the bottom of the slide. The bottom equation, known as the wave equation, was previously known to describe mechanical waves such as sound or a vibrating string. This is how Maxwell came to recognize light was a wave mathematically. It is not a coincidence that the speed of light appears in these top two equations. It was a number of years before the scientific community would completely accept that the mathematics here is a description of light that is in fact correct. Light was known to behave like a wave. Light could be diffracted. Light was known to exhibit constructive and destructive interference. Mechanical waves are transported through a physical medium. What physical medium was light traveling through? Light travels through space, an almost perfect vacuum. Is there a medium in empty space? Some thought that a medium is required and set out to look for it. It was given a name. It was called the ether. Here we see a mathematical solution to the top equation for the E field from the previous slide, which is a sine wave. The equation for the magnetic field B has a solution which has exactly the same form. This solution is for a sine wave of frequency f. The wave has the property that when you multiply the wavelength of light by this frequency f, you get c. The speed at which the wave travels is equal to the product of its wavelength and its frequency. Waves with more complicated shapes may be created by adding together various combinations of sine waves with different frequencies and different amplitudes. All the solutions to the wave equation can be constructed by linear combinations of these sine waves. We turn now to the concept of relative motion and inertial reference frames. This slide shows two Cartesian coordinate systems, S and S'. Let's assume that the coordinate system defined as S on the left is at rest. A stationary object at a particular point having coordinates x, y, z will not see its coordinates change as time progresses. Let's choose the second reference system, S' on the right, to have its y and z axes coincide with the y and z axes of system S. The same location in space that we call x, y, z in system S will have coordinates x prime, y prime, z prime in system S prime. By choosing the y and z axes in both systems to coincide, we force y prime to equal y and z prime to equal z for all times. We make this choice to simplify the discussion that follows as we look at relative motion between the two systems that is directed only along the x and x prime axes. The x and x prime axes are chosen to be parallel and such that the origins of s and s prime coincide at the instant in time we define as t equals 0. We set the coordinate system s prime in motion to the right at a constant velocity u with respect to s. As time progresses, the origin of s prime will be further and further to the right of the origin of s. Now consider a point x prime, y prime, z prime that is at rest in system S prime. What would the coordinates be for this same point in space measured by the coordinate system of S? Take a moment to convince yourself that x equals x prime plus ut. Take another moment to convince yourself that if instead we have a point x, y, z that is at rest in system S, then in system S prime we have x prime equals x minus ut. The two coordinate systems shown on this slide are called inertial reference frames because they are both moving at a constant velocity. System S has the constant velocity of 0. System S prime has the constant velocity u to the right. In all the discussions that follow in this video, we will only concern ourselves with inertial reference frames. When we are looking at two inertial reference frames in this video, we will use the convention that the relative velocity between them is u. We will reserve the use of the variables v and v prime to describe the velocities of objects at particular points from within one of the two coordinate systems. If the variable x, y, z, v, or t does not have a prime after it, then we mean the variable has a value as measured in the coordinate system S. If the variable x, y, z, v, or t has a prime after it, then we mean the variable has a value as measured in the coordinate system S prime. The Galilean or the Newtonian view of reality is that space is fixed and that time marches forward in all locations of space at the same rate. We set our clock to 0 anytime we like, but then it advances at the same rate everywhere. In an abstract sense, we can consider an event to be a particular location at a particular time. From the Newtonian point of view, we can therefore define a set of transformations for an event between the coordinate systems as follows. From S to S prime, we have x prime equals x minus ut, y prime equals y, z prime equals z, and t prime equals t. From S prime to S, we have x prime equals x plus ut, y equals y prime, z equals z prime, and t equals t prime. There is a symmetry in these transformations. To change the direction in which you are making the transformation, all you have to do is change the sign in front of the u. The situation becomes more complicated when one recognizes the requirement from Maxwell's equations that the speed of light c must be the same in both of the inertial reference frames S and S prime. This is a conceptual problem when considering reference frames that have a large difference in relative velocity. This is not a problem, however, in a practical sense, as long as the value for u is much, much less than c. It was known as early as 1676 that the speed of light, although enormous, is not infinite. This was discovered by observing the variation in the apparent motion of Jupiter's moon Io with the distance between the Earth and Jupiter. What happens when we consider the apparent speed of the same beam of light from both S and S prime? If the beam of light moving towards the right has a speed of c in reference frame S prime, doesn't it have to have a speed of c plus u when viewed by an observer in reference frame S? This is how relative velocity is computed in Newtonian mechanics. This is how objects in motion behave in our everyday experience. But if Maxwell's equations are correct, then the same beam of light must be c in both S and S prime. Scientists and mathematicians considered and struggled with this apparent paradox for many years. A way out of the paradox was eventually found through the work of many physicists, including Hendrik Lorentz. We will now look at the mathematics that would make Maxwell's equations consistent across all frames of reference. On this slide and the next two slides, we derived the Lorentz transformations using mathematics alone. We recognize that the world behaves in a consistent way. A physical law that is true today is true tomorrow. An experiment that is conducted in the United States will have the same results as an experiment conducted in China, as long as the two experiments are conducted in the same way. We impose the requirement that c is constant in both of the reference frames S and S prime. We assume a linear solution to the transformation for position in x or x prime between S and S prime, and the inverse transformation between S prime and S. We give them the same general form as the result expected for Newtonian mechanics, except that we assume the Newtonian result must be multiplied by some other known expression that is the same in both directions. The symmetry of the situation requires that this unknown expression must be the same for either direction of transformation. We call the unknown expression gamma, and we use the Greek letter gamma to represent it. Our task then is to solve for gamma, requiring that c be constant in both S and S prime. Note the symmetry still present in the transformations. The only difference between the transformations in opposite directions is the sign of u. For the light beam in both reference frames, we use the fact that distance equals velocity multiplied by time to obtain expressions for t and t prime in terms of c and x or x prime respectively. We substitute the expression for t or t prime back into the expected result for the value of x or x prime. Once this substitution has been made, we can factor out the common x on the right side of the expression for x prime, and likewise the common x prime on the right side of the expression for x. Now we multiply the equations for x and x prime together. The product of the left side will still be equal to the product of the right side. As long as we are looking at any time after t or t prime equals 0, we can be confident that the product of x times x prime is not 0. Now the product x prime is found on both sides, so we can divide through by it. We recognize the product of the sum and difference of two identical terms is equal to the first term squared minus the second term squared. Rearranging the expression to solve for gamma gives us 1 divided by the square root of the quantity 1 minus u squared divided by c squared. This is the key result that makes the Lorentz transformations work. Gamma is called the Lorentz factor. Use of gamma to represent the expression 1 divided by the square root of the quantity 1 minus u squared divided by c squared is a common convention in discussions of special relativity. I will only selectively use this convention in the remainder of this video so that we will not lose sight of where u and c appear in the mathematics. Now that we have found x prime equals the quantity x minus ut divided by the square root of the quantity 1 minus u squared divided by c squared, we can proceed to find the expression for t prime in terms of t, u, x, and c. We have x prime equals gamma times the quantity x minus ut, which also equals c times t prime. We can substitute ct for x in the expression x minus ut, and then divide both sides of the result to get an expression for t prime, which is the expression t minus the quantity u times x divided by c squared. Our algebraic derivation of the Lorentz transformations is complete. The expression for x prime in terms of x, u, and c is x prime equals the quantity x minus ut divided by the quantity square root of 1 minus u squared over c squared. The expression for t prime in terms of t, u, c, and x is shown here. We have t prime equal to the expression t minus ux divided by c squared divided by the square root of the quantity 1 minus u squared over c squared. We also, by choice of the alignment of the coordinate systems s and s prime, have y equals y prime and z equals z prime. This is the complete set of equations for x prime, y prime, z prime, and t prime in terms of x, y, z, and t. The Lorentz transformations can also be derived using a physical argument using a spherical wavefront of light emanating out in all directions from a point source at the origins of the coordinate systems s and s prime at the instant when the origins coincide at t equals t prime equals 0. This slide shows the spherical wavefront growing at later times in both coordinate systems. A particular point on the spherical wavefront is an event x, y, z, t in system S as shown. The same point is also an event x prime, y prime, z prime, t prime in system S prime as shown. Since it is the same point on the same spherical wave, we are looking at the same event. It is just that the event has 4 coordinates that are different but equivalent from the points of view of S and S prime. We know from geometry expressed in Cartesian coordinates in 2 dimensions that the equation of a circle is x squared plus y squared equals r squared. In 3 dimensions, the equation of a sphere is x squared plus y squared plus z squared equals r squared. In both cases, r is the radius. The diagram on this slide shows the radius of the spherical wavefront in both S and S prime growing rapidly as the light spreads out with speed c. This slide shows the equations for the spherical wavefronts in S and S prime. The wavefront moves at a constant velocity c in both reference frames. The spherical shape in both reference frames must be maintained. The apparent paradox of this requirement is reflected in the previous slide. In 3 dimensions, it is not possible to visualize such a sphere. This diagram is as close as we can come. The requirement that r equals c times t and r prime equals c times t prime for the spheres can be used to obtain the same result as the derivation of the Lorentz transformation shown previously. The spherical wavefront in S is represented by the equation x squared plus y squared plus z squared equals r squared, which also equals c squared times t squared. The spherical wavefront in S prime is represented by the equation x prime squared plus y prime squared plus z prime squared equals r prime squared, also equal to c squared times t prime squared. This alternate derivation for the Lorentz transformations now follows a similar argument to the first derivation. By choice of coordinate systems, we have y prime equals y and z prime equals z. The relationship between x and x prime should be linear and should reduce to the Newtonian or Galilean transformation for small values of u. The transformation for obtaining x prime from x, u and t, and the transformation for obtaining x from x prime, u and t prime should be symmetrical, and our task becomes finding the expression for gamma, the same gamma as before, that satisfies the spherical wavefront equations in S and S prime on the previous slide. We substitute the expression for x prime, gamma times the quantity x minus ut, into the expression for x. Gamma times the quantity x plus u times t to get x equals gamma times the expression gamma times the quantity x minus ut plus u times t prime. We rearrange this expression to solve for t prime. We divide through by gamma and then add and subtract terms to get the term ut prime on the left by itself. We divide through by u and then rearrange to get a term with t in it and a term with x and u in it. We use this expression for t prime on the next slide. We have assumed the form for x prime as gamma times the expression x minus ut. We have the expression for t prime from the bottom of the previous slide. We have y prime equals y and z prime equals z. We now substitute the expressions for x prime, y prime, z prime, and t prime into the equation for the sphere in S prime. X prime squared plus y prime squared plus z prime squared equals c squared times t prime squared. This gives us the quantity gamma times x minus ut all squared plus y squared plus z squared equals c squared times the quantity gamma times t plus quantity 1 minus gamma squared times x divided by gamma u all squared. We multiply all these terms out on both sides of the equation as shown at the bottom of the slide. We rearrange the complicated expression from the bottom of the previous slide, where we can, to collect terms with common factors of x squared and t squared. When we do this, there are two cross terms left over, as well as terms in y squared and z squared. Our equation now has no primed terms in it. This equation must therefore represent the identical event for the point on the sphere as viewed from reference frame S. This equation, by definition, has no prime terms in it either. This equation is x squared plus y squared plus z squared equals c squared t squared. We can set the coefficients for t squared terms equal to each other. When we do that, we have a simple expression for gamma squared in terms of u squared and c squared. Rearranging this expression to solve for gamma, we get the same result as before. Gamma equals 1 divided by the square root of the quantity 1 minus u squared divided by c squared. We have now seen two ways to derive the Lorentz transformations. The first method was just algebra. In the second method, we looked at spheres whose centers were at the origins. I would like to digress for a moment and talk about spheres and coordinate systems. When considering only a sphere in 3 dimensions, we recognize that there exists a symmetry such that we could have rotated the x, y, and z axes in any number of different directions and we would still have a sphere. One could call any of these rotations a transformation in 3 dimensions from a reference frame of x, y, z to a reference frame of x prime, y prime, z prime. The radius of the sphere does not change. A sphere has the property that x squared plus y squared plus z squared equals r squared, or equivalently, x prime squared plus y prime squared plus z prime squared equals r squared. The radius of a sphere does not vary when you rotate coordinate systems. Similarly, in 2 dimensions, if you rotate a circle, you do not get a different radius. Equivalently, if the circle is not rotated, but instead you rotate the x and y axes, you still have the same radius. The Pythagorean theorem still holds. X squared plus y squared equals r squared, or equivalently, x prime squared plus y prime squared equals r squared. What happens if you consider 4 dimensions? In our second derivation of the Lorentz transformations, we had spheres represented by the equations x squared plus y squared plus z squared equals r squared equals c squared t squared, and x prime squared plus y prime squared plus z prime squared equals r prime squared equals c squared t prime squared. We could rewrite these equations as x squared plus y squared plus z squared minus c squared t squared equals 0, and x prime squared plus y prime squared plus z prime squared minus c squared t prime squared equals 0. X, y, z, and t, and x prime, y prime, z prime, and t prime are the same event. The event is identified by a different set of 4 numbers depending on whether you are an observer in S or an observer in S prime. For the simplest case possible, a sphere at the origin as presented here, the result of the operation where you square and sum the values of the position coordinates and then subtract the square of the product of c and the time coordinate, always gives you the same value. Here, that value is 0. But there are other events where this set of operations will not sum to 0. It is beyond the scope of this video to provide a proof, but it turns out that a Lorentz transformation from x, y, z, t to x prime, y prime, z prime, t prime always gives you the same value for the sum of the 4 terms shown here. This is where the idea of 4-dimensional space-time comes from in special relativity. By analogy, given the form of the equation here, whose value does not vary when you perform the Lorentz transformation, you can consider the set of 4 Lorentz transformations to be a rotation of space-time in 4 dimensions. By the way, the derivations in this video that assume that the y and z axes lined up can be proven to be true also for any angle of orientation between S and S prime. This would require the use of matrices, algebra that is unnecessarily messy, and is also beyond the scope of this discussion. By the 1880s, scientists were looking for evidence of the existence of the ether. They reasoned that if light is a wave, then light needs a medium to travel through. There should be some way to detect this ether, as the Earth revolves around the Sun very nearly in a circle with a radius of 93 million miles in a period of 365 days. This corresponds to a speed of 18 miles per second in a direction that would vary by 360 degrees in a year. The Earth also spins on its axis once a day, so any experiment conducted on its surface would be making measurements that are in different directions at different times of day. The starting point was the idea that light would travel at the speed c with respect to the stationary ether. Before accepting Maxwell's equations, Wood should conduct experiments to look for evidence of differences in the speed of light in different directions. If the Sun is at rest in the ether, then there should be a headwind that is observable because of the motion of the Earth around the Sun. There were many experiments conducted by many different people to detect the ether wind both before and after the most famous of all that was conducted in Cleveland by Michelson and Morley in 1887. This slide is a schematic representation of the Michelson-Morley experiment. A coherent light source shines upon a half-silvered mirror oriented at 45 degrees to the light beam, so that half of the light is transmitted through in a straight line and half of the light is reflected at 90 degrees. The split beams then travel an identical distance, or as nearly an identical distance as the construction of the equipment will allow, to two more mirrors perpendicular to the beams. The split beams then return to the same half-silvered mirror, where a portion of them are recombined after transmission and reflection again to a target screen where the interference pattern of the split beams can be observed. If light traveling in perpendicular directions travels at different speed because of the ether wind, then there should be a shift in the interference pattern as the apparatus is rotated through 90 degrees. This slide is an old photograph of the actual equipment used in the Michelson-Morley experiment. The light source, light detector, and mirrors were mounted on a granite platform that was then floated on a pool of mercury so that the rigid platform could be rotated with a minimum of vibration. This slide is a more detailed schematic of the apparatus for the Michelson-Morley experiment. We will use the diagram to develop the algebra to analyze the experiment. The setup is assumed to be moving horizontally in the positive x direction at constant velocity u. For the moment, we do not assume use of the Lorentz contraction because the experiment is designed to reveal evidence of the stationary ether. The motion to the right is equivalent to the headwind of the ether wind blowing towards the left in the diagram that was shown 2 slides ago. If you will, this diagram is analogous to the S reference frame. The previous diagram is analogous to the S' reference frame. We analyze the light beam assuming Newtonian mechanics. The vertical distance from the half-silvered mirror B to the mirror C at the top of the diagram is L. The horizontal distance from the half-silvered mirror B to the mirror E at the right of the diagram is also L. The fact that the two distances L cannot really be made exactly identical in practice is not important because the experiment is actually looking for shifts in the interference pattern as the apparatus is rotated. A 90-degree rotation of the apparatus interchanges the roles of the mirrors C and E. If there is little or no shift in the interference pattern upon this rotation, that is a null result, then the experiment will be supporting the idea that the speed of light is constant independent of the direction of motion of the Earth. Each of the arms from B to C and from B to E are several meters long. If the wavelength of light is approximately 3 times 10 to the minus 7th meters, and since the Earth's speed in orbit is approximately 1/10,000th of the actual speed of light, we know that the equipment has the sensitivity required to detect the ether wind by observing shifts in interference patterns at the detector D/F. This slide is a picture of what the interference fringes look like when conducting the Michelson-Morley experiment. We start by analyzing the light beam traveling in the horizontal direction from B to E and then back to B. The speed of light is taken to be c in the stationary ether. Moving to the right, the apparent velocity of the beam is c minus u. The mirror E moves to the right while the light beam is catching up to it. On the return trip back from B, the apparent velocity of the light beam is c plus u. The time t1 for the light beam to travel to the right and the time t2 for the light beam to travel to the left are shown at the top of this slide. The total round-trip time for the horizontal light beam is t1 plus t2 and equals 2 times L times c divided by the quantity c squared minus u squared. We then divide the numerator and the denominator by c squared. We will compare the result in this form to the round-trip travel time for the vertical light beam on the next slide. Now let's turn our attention to the light beam traveling in the vertical direction. The path of the light beam from B to C on the previous slide forms the hypotenuse of a right triangle. The vertical side of the triangle is L, and the horizontal side of the triangle is formed by the motion of the whole apparatus traveling to the right in the stationary ether with speed u. If the time for the light beam to travel from B to C is called t3, then we can compute t3 using the Pythagorean theorem. We have the quantity c times t3 squared equals the sum of L squared and the quantity u t3 squared. We collect all the terms with t3 on one side and take the square root to get the equation for t3 shown at the bottom of the slide. Looking again at the diagram of the apparatus, we see a similar right triangle and recognize that the return time from C back to B, which by then has moved to the right and is shown in the diagram as B prime, is also t3. So the total time to travel from B to C and back is 2 times t3. This is 2 times L divided by the quantity square root of c squared minus u squared. We divide the numerator and the denominator of this result by c to get it in a similar form as the result for the horizontal beam as shown in the middle of the previous slide. Now for the key result from the Michelson-Morley experiment. There appeared to be no shift in the interference fringes when the apparatus was rotated. The analysis we just completed using Newtonian mechanics shows that the two different paths taken by portions of the initial beam should have taken different times. 2 times t3 does not equal the sum of t1 and t2. The expressions for 2 times t3 and for t1 plus t2 differ by a factor of 1 over the square root of the quantity 1 minus u squared divided by c squared. This factor is gamma. Efforts to find the ether wind did not stop with the Michelson-Morley experiment. Similar experiments were conducted outdoors and on mountaintops in case somehow the ether wind was being blocked. Lorentz suggested a possible solution to the dilemma. If material bodies contract when they are moving, and that contraction is only in the direction of motion, then the times of travel for the horizontal and vertical light beams in the Michelson-Morley experiment would become identical. The length of an object in the dimension parallel to the motion could be given a value equal to the rest length times the square root of the quantity 1 minus u squared divided by c squared. This compensates for the difference between the denominators of the two expressions for time. Note also that when u is much, much less than c, then the two expressions for time approach each other even without considering this Lorentz contraction. In both cases, the denominators approach 1. There is one more key idea at play here. It concerns the rate at which time progresses for the stationary observer versus the rate at which time progresses for the observer moving to the right with velocity u. For the observer moving with velocity u, the time for the vertical light beam to travel to mirror C and back is 2 times L divided by C. For the stationary observer, we have this time as 2 times T3, or 2 times L divided by C, all divided by the quantity square root of 1 minus u squared divided by c squared. This factor in the denominator is always less than 1, which means that time is greater for the stationary observer than for the moving observer. To the stationary observer, lengths contract and clocks slow down. We have just shown that a consistent explanation for the null result for the Michelson-Morley experiment is mathematics that requires, for a stationary observer, that lengths are contracted in the direction of motion and that clocks slow down. This is not particularly intuitive. This is one reason why there were 18 years between the experiment and the publication of Einstein's paper on special relativity in 1905. Lorentz published a paper in 1904 on the covariant formulation of electrodynamics. This showed the transformations between electric fields and magnetic fields consistent with Maxwell's equations based upon any frame of reference using the Lorentz transformations, which we have already derived in this video. Electric fields and magnetic fields are actually one electromagnetic field. No problem with C being a constant to all observers here. But this too remained controversial. In 1915, Einstein generalized the theory of relativity to include accelerated reference frames and gravity, which he argued are essentially the same thing. Even in 1921, when Einstein was awarded the Nobel Prize in Physics, it was for the photoelectric effect, not for the theory of relativity. With this slide, let's talk some more about the idea of clocks slowing down. To the stationary observer, a vertically oriented light meter clock will have a light beam traveling a longer zigzag path, like the one in the diagram of the apparatus for the Michelson-Morley experiment, than the path seen by the moving observer. A diagram of such a light meter clock will be shown on the next slide. Before looking at the whole clock, though, let's consider just a simple right triangle. In the right triangle shown here, the zigzag light beam covers a distance c in 1 second. The vertical leg of the triangle is a distance of the square root of quantity c squared minus u squared in 1 second. This is a shorter distance than the hypotenuse of the triangle. So it appears to the stationary observer that the time to get to the top for the path seen by the moving observer should be less than 1 second. If the moving observer does not see it that way, then his clock must be running slower. Let's now tie up a loose end and show that the analysis shown between this slide and the previous 3 slides give us the same expression for the transformation of x to x prime we derived earlier. Consider that we have a meter stick or a ruler or any similar object of length x prime when stationary. When this object is moving to the right with velocity u, as seen by the stationary observer, it will be foreshortened. To an observer moving with a meter stick, it will be stationary. If one end is at x equals 0, as seen by the observer and the moving reference frame, then the other end is at x equals x prime times the quantity square root of 1 minus u squared divided by c squared. Divide both sides of the quantity square root 1 minus u squared divided by c squared squared, and you have the Lorentz transformation equation for x prime we are looking for. This slide is the diagram of the Einstein light clock. This concept is very similar to the apparatus in the Michelson-Morley experiment and is easier to visualize than a mechanical clock. When Einstein did all of his thought experiments to come up with a theory of special relativity, this is the kind of clock he envisioned. This idea makes it easier to keep track of what is going on when one is forced to keep c constant. The Lorentz contraction for length in the direction of motion is fairly easy to visualize, even though we do not observe it for objects in motion that we encounter on an everyday basis. Let's take a moment to look at something that is not easy to visualize. The behavior of time is required by the fourth of the equations in the Lorentz transformation. Recall that the equation for t prime is the one that appears on the upper right in this slide. The numerator is unusual. The rest is just the Lorentz factor gamma. Earlier, we defined an event as a specific set of 3 space coordinates and 1 time coordinate. An event requires 4 values grouped together, x, y, z, t. Consider 2 events, x1, y, z, t0, and x2, y, z, t0, that are simultaneous to the stationary observer in S. The simultaneity of the 2 events is indicated by the same value t0 for the time. We can use the fourth equation in the Lorentz transformation to calculate the times for the same event as observed when moving to the right along the positive x-axis with constant velocity u. This is our reference frame S prime as before, and because of the fact that we choose y prime equals y and z prime equals z, we need only calculate the t1 prime for the event at x1 in S and the corresponding t2 prime for the event at x2. We plug in the values for x1, t0, and x2 into the transformation to get t prime and get the results shown in the middle of this slide for t1 prime and t2 prime. When we subtract t1 prime from t2 prime, we get the result shown at the bottom of the slide. Once again, like for the equation at the top right of the slide, the denominator just gives us a coefficient of gamma in front of what is now a very interesting numerator. The interesting part is that the numerator is not 0. The size of the numerator grows as x2 becomes further away from x1. The variable t0 has disappeared. This is fortunate because we would hope not to have the behavior be different because of our choice of t0. What we have here is a loss of simultaneity. 2 events in S that are simultaneous are not simultaneous when viewed in S prime. They are not at the same location. Of course, if they are at the same location, they would in that case in fact be the same event. This concept is called failure of simultaneity at a distance. Not only do clocks run at different speeds in S and S prime, 2 events that are simultaneous in one of the reference frames cannot be simultaneous in the other. The discrepancy is greater the further apart in space the events are. This slide summarizes the Lorentz transformation equations for position and time on the left. These are the same transformations from S to S prime. This slide also summarizes the reverse Lorentz transformations for position and time on the right. These reverse transformations are from S prime to S. These equations for going both ways are shown here all together to remind us of the symmetry inherent in them. You can obtain the inverse transformation simply by replacing a u with minus u everywhere and adding or removing the primes from x, y, z, and t. In the next section of this video, when we are going to look at the complete symmetric elastic collision to derive the equation for the relativistic increase in mass with velocity, we need to recognize the symmetry in the set of equations here as part of that derivation. We have found already that motion in the S prime reference frame, as viewed from the stationary reference frame S, has the clock moving more slowly. This is true for the components of motion both in the x direction and in the y direction. But the apparent change in length as seen from the S reference frame applies only to the x direction. On this slide and on the next slide, we use the Lorentz transformation equations to calculate the formula for velocity in the x direction and then the formula for velocity in the y direction, respectively, for the observer in S. In both cases, the velocity equation is found by dividing the expressions for distance, x or y, by the expression for time. V sub x equals x divided by t, and v sub y equals y divided by t. Here, on this slide, we are looking at the x direction. Note that in reference frame S prime, we are calling the velocity in the x direction v sub x prime. This, of course, means that x prime equals v sub x prime t prime. The substitutions are performed as shown in the middle of the slide. The factors of gamma, which are common to numerator and denominator, cancel out, and the result is shown at the bottom. The expression in the denominator is interesting. As we would expect, if u is much, much less than c, then the denominator approaches 1, and we have the Newtonian result. It may be worth a look here again at v sub x after we do the similar calculation for v sub y on the next slide. Here we are looking at motion in the y direction only and calculating the velocity in v sub y for the stationary S reference frame. We know that y equals v sub yt and y prime equals v sub y prime t prime. When we divide y by t, we can substitute v sub x prime t for x prime in the expression for t in the denominator. Since the motion we are looking at now is only in the y and y prime direction, we know that v sub x prime equals 0. This simplifies the denominator considerably. There is a common factor of t prime in the numerator and denominator. The expression square root of quantity 1 minus u squared divided by c squared flips up into the numerator, and we have the simple result as shown. This answer is reasonable as we see the apparent velocity v sub y in S is slower than v sub y prime in S prime. This is consistent with a clock appearing to move more slowly. We see that v sub y approaches v sub y prime when u is much, much less than c. We are now ready to move on to the next to last item on our agenda, derivation of the relativistic mass equation. We will make use of this expression here for v sub y to do it. Henri Poincaré, a contemporary of Lorentz and Einstein, summarized the situation at the time by saying, according to the principle of relativity, The laws of physical phenomena must be the same for a fixed observer as for an observer who has a uniform translation relative to him, and that we have not, nor can we possibly have, any means for discerning whether or not we are carried along in such a motion. We are confident that we can do this because our inability to detect absolute motion has been established experimentally by Michelson and Morley and by others. We now derive the relativistic mass equation assuming the law of conservation of momentum and the law of conservation of energy using the guideline just stated. We assume that momentum is a vector and that the direction of the momentum vector is the same as the direction of the velocity vector. We apply these situations to the specific case of an elastic collision. The diagram at the bottom of this slide is taken directly from the Feynman Lectures in Physics, Volume 1, Chapter 16. The derivation in this video uses the idea that mass is the ratio of momentum to velocity. It does not use the idea that mass is the ratio of force to acceleration. We consider two identical objects moving towards each other at the same speed but in opposite directions. We consider an elastic collision in which the total kinetic energy of the objects is conserved. There are no dissipative forces such as friction at play. In the diagram at left is a picture of the situation when object 1, moving from the left, is not traveling exactly towards object 2, moving from the right. The angle theta is indicated is the angle between the entry path of object 1 and the exit path of object 2. Because of the symmetry in the situation, theta is also the angle between the entry path of object 2 and the exit path of object 1. In the diagram at right is the exact same collision except that we have rotated the coordinate system so that the positive x direction splits the angle theta in half. We consider this reference frame S to be the rest reference system. In this reference system, the total momentum of the two objects is 0. Object 1 approaches the collision from the bottom left, and object 2 approaches the collision from the top right. With this choice of reference frame, the x components of the motion of both objects are unaffected by the collision. On the next slide, we're going to look at the same collision from moving reference frames, in which one or the other of the objects has motion only in the vertical direction. The reference frames will then be moving in the x direction at the same speed as one or the other of the objects. The diagram on this slide is also taken directly from the Feynman Lectures on Physics, Volume 1, Chapter 16. On the left, the same elastic collision is shown from reference frame S', which, compared to the reference frame S, is moving to the right with an identical speed as the x component of the speed of object 1. The motion of object 1 is now in the vertical direction only, and we denote the speed in y' as w. Object 2 still approaches the collision from the upper right and exits to the upper left. The path that object 2 takes in S' has a shallower angle with respect to the x' axis than the angle theta divided by 2 in the diagram on the previous slide. We denote this new angle as alpha. The x' component of motion for object 2 is to the left with speed u. On the right side of the slide, the same elastic collision is shown from a third reference frame S', which instead is moving to the left with an identical speed as the x component of the speed of object 2 in S. The left and right sides of the diagram are symmetric. In A, the reference frame S' is moving to the right. In B, the reference frame S'' is moving to the left. In S prime prime, it is object 2 that has motion only in the vertical direction, and object 1 that has an x prime prime component of motion. In S prime prime, the direction of the x prime prime component of motion of object 1 is to the right with speed u. The path that object 1 takes in S prime makes the same angle alpha, this time with respect to the x prime prime axis. The y prime prime motion has the speed w. In A and B here, the magnitudes of u and w are the same. The directions are opposed. We have designed the collision using the previous two slides. We are using an elastic collision so that no kinetic energy is lost or transferred between the objects. Because the identical objects have the same mass and the same speed in S, they both must have the same speed before and after the collision. This is where the symmetry in the diagrams for S, S prime, and S prime prime comes from. What is the vertical velocity given by u times the tangent of the angle alpha? If we knew that, then we could use conservation momentum in the vertical direction to get the correct expression for the momentum. It is obvious that momentum is conserved in the horizontal direction because that component is unchanged for both particles and all three reference systems, S, S prime, and S prime prime. We need only to consider the vertical component of the velocity as shown here in the right triangle. Looking at S prime as the base reference system, we can use our previously derived expression for the apparent relativistic velocity in the y direction. From this, we know u times the tangent of alpha has to be w times the quantity square root of 1 minus u squared divided by c squared. Recall that the vector for momentum p must be the vector given by a scalar we call the mass in the direction of the vector v, m sub v, times the velocity vector v. We have vector p equals m sub v times vector v. The change in the vertical momentum of the vertically moving particle has to be 2 times the mass in the vertical direction, m sub w, times w. We have delta p equals 2 times m sub w times w. The change in vertical momentum of the obliquely moving particle is given by a delta p equal to 2 times the mass m sub v times w times the square root of 1 minus u squared divided by c squared. These two changes in momentum have to be equal to each other. The total vertical momentum is 0 whether you are in S, S prime, or S prime prime. Dividing the expression with m sub w in it by the expression with m sub v in it, we get the quantity square root of 1 minus u squared divided by c squared. We finish by looking at what happens when we take the limit where w approaches 0. Looking at our right triangle with hypotenuse v, we see that the vertical leg shrinks to a length of 0 and v approaches u. When w approaches 0, the mass in the w direction, m sub w, has to approach the rest mass, and we call this m sub 0. With the vertical leg shrinking, v approaches u, implies the mass in the direction of the velocity is approaching the mass in the direction of u. We call this m sub u. Multiplying both sides by m sub 0 gives us our final result at the bottom. M sub u equals m sub 0 divided by the quantity square root of 1 minus u squared divided by c squared. Looking at this expression for relativistic mass increase, we see that the denominator becomes smaller as u becomes a significant fraction of c. In the limit where u approaches c, the denominator approaches 0, and the relativistic mass becomes infinite. This slide is a graph of typical experimental data showing the relativistic mass increase, which confirms the theoretical result from the previous slide. Along the horizontal axis, we have the ratio of the velocity of a particle to the velocity of light. On the vertical axis is the ratio of the measured mass of a particle to its known rest mass, m sub 0. Data such as this has been taken since the early 20th century, starting with the electron and then moving on to the proton, and then other heavier and more exotic particles as physicists started building bigger and bigger particle accelerators to study them. We are almost done deriving E equals mc squared. Given the formula for relativistic mass, we start with a differential expression for energy. The differential for energy is equal to force times the differential for distance. Force is the rate of change in momentum with respect to time. Regrouping the differentials gives us the differential for momentum times the velocity. Since momentum equals mass times velocity, we can use the rule for differentiating the product of two functions to say the differential for momentum equals the mass times the differential for velocity plus the velocity times the differential for mass. Substituting into the expression dE equals V dP gives us dE equals mv dV plus v squared dN. We will use this result later in the last slide. We differentiate the expression at the top of the slide for the relativistic mass with respect to velocity. We treat the expression as a function of velocity so that we can use the chain rule. We then split the term quantity 1 minus v squared over c squared, all raised to the minus 3/2 power, so that we have the original expression for the relativistic mass in terms of m0 as a factor that we can go ahead and replace with m. We continue rearranging the result as shown at the bottom. We flip the numerator and denominator from the expression at the bottom of the last slide, getting rid of the exponent minus 1. The result is the derivative of mass with respect to velocity equals m times v divided by quantity c squared minus v squared. We multiply both sides of the equality by quantity c squared minus v squared and also by the differential for velocity dv. We have c squared times the differential for mass minus v squared times the differential for mass equals m times v times the differential for velocity. We substitute this expression for m times v times the differential for velocity into the expression for differential energy from the previous slide. The two terms v squared times the differential for mass cancel. We have the differential for energy equals c squared times the differential for mass. We can integrate this expression from any starting energy to any finishing energy corresponding to any starting mass to any finishing mass. If the lower limits for the definite integral are 0 on both sides of the equation, then we have E equals mc squared. To summarize, this video has shown the entire derivation of the most famous equation in science. All of the details have been included. The starting assumptions in the mathematics have been shown. Some historical perspective has been given for the theoretical requirement and the experimental result that the speed of light is a constant for all observers. In order to get this result, it was necessary to understand the Lorentz transformations and a significant portion of the theory of special relativity. As I set about the task of making this video and understanding the material well enough to explain it to others, it became apparent why I had not before seen a full derivation of E equals mc squared and this level of detail all in one place. I hope you enjoyed watching the video and that discussion was clear enough to follow for those of you with no prior exposure to special relativity. A couple of comments on the references I used to make this video. The Wikipedia article on the Lorentz transformation is one of many excellent technical articles provided by this free encyclopedia resource that is continuously refreshed. Please consider supporting them with an annual donation. I do. I bought my copy of the Feynman Lectures as a freshman in college in 1973. These lecture notes were then, and still are, a primary source of lucid explanation of physics from probably the most talented physicist of the second half of the 20th century. Graduate students in physics used these notes to study for their PhD qualifying exams. The third source was my AP Physics text from high school. After rereading the foreword to the fourth edition, I went and found a used copy of the third edition from 1964 on Amazon.com. It pays to go back to the era when American educators were reacting to the challenges imposed by Sputnik if you are looking for rigorous mathematics in your study of physics.